Many solvents have been presented as green, but none of them is really fully green. The solvent desirability is influenced by many criteria, which sometimes are contradictory. Occupational health, safety, environment, which concerns air, water, and carbon footprint, industrial issues linked with boiling point, cost, procurement, and other constraints. Besides, greenness depends on the application. Criteria for a solvent for paint stripping are not the same than for chemical synthesis. This is why some pharma companies have elaborated solvent guides in order to help chemists in the selection of the most desirable solvents. These guides reflect the policy of the company or institution based on the local constraints, the accidents, and their culture. Not surprisingly, they differ by their structure and the relative weighing of criteria. As part of the Work Package 1 of CHEM21 project, we made a survey of solvent selection guides and proposed a methodology to establish and compare the ranking of solvents. I presented this in the module entitled Survey of Solvent Selection Guides. A combination of HSC criteria for each guide gives a figure and a color code for the three guides which did not give a clear overall ranking, and a comparison of the colors for each solvent shows the degree of convergence between these guides. According to this survey, 67% of the 51 solvents considered are scored with low level of ambiguity, as recommended, problematic, hazardous, or highly hazardous. This has been published in Green Chemistry in 2014. The glass can be seen as two-thirds full or one-third empty. One-third of solvent could not be ranked by this simplified system. This is not very surprising, as these borderline solvents are often green with respect to one criterion and not for the others. This also reflects the different perceptions and cultures of the institutions. For the elaboration of CHEM21 solvent guide, we needed a methodology permitting a ranking of these intermediate solvents. This methodology should work with the 67% of solvents having a clear ranking and should also be able to give a greenness assessment of any solvent, in particular bio-derived solvents. The methodology we elaborated is quite simple and based on GHS statements and some physical data, which can be collected from any safety data sheet. Like for the Solvents Guide survey, we elaborated one safety, one health, and one environment score, each from 1 for the best to 10 to the worst. And we associated a color code, 1 to 3 green, 4 to 6 yellow, 7 to 10 red. If the data are incomplete, the corresponding score is 5. A solvent ranking by default is obtained by simply counting the safety, health, and environmental score. One score superior or equal to 8 or two scores superior or equal to 7 flags the solvent as hazardous. One score equal to 7 scores the solvent as problematic, as well as two scores between 4 and 6. In other cases, the solvent is considered as recommended. How does it work? The first task is to collect some data, boiling point, flash point, autoignition temperature, and the GHS statements from the safety data sheets. Note that the GHS statements may vary depending on the supplier. In these cases, the advice of an occupational hygienist is useful. The safety score is mainly based on the flash point, with the same limits than the GHS statements, but with a finer distinction when the flash point is lower than 22 degrees. Increments are added for each of the following properties: autoignition temperature lower than 200 degrees, high resistivity, ability to form explosive peroxides. For example, diethyl ether with a flash point of -45 degrees has a basic safety score of 7, but as its autoignition temperature is 160 degrees, as it is resistive and forms hazardous peroxide. Its final safety score is 10. The health score derives from the most stringent H300 statements according to this table. The CMR solvents of category 1A or 1B are scored 9, and the CMR of category 2, such as toluene, dichloromethane, and THF, are scored 6. 1 is added to this score if the boiling point is lower than 85 degrees, to take into account the highest occupational risk of more volatile solvents. For benzene or dichloroethane, one ends up with 10. The environment score is very qualitative. It is based on both the DHS H400 statements and the boiling point. Boiling point lower than 50 degrees or higher than 200 degrees gives a score of 7, as well as the H400, H410 or H411 statements. For example, diethyl ether is ranked 7 because of its low boiling point, and heptane is ranked 7 because of its ecotoxicity. Let us apply the ranking methodology. With the safety, health and environmental score in hand, the ranking by default is immediately obtained. Ethyl acetate with only one score of 5 is recommended. Methyl THF with two scores between 4 and 6 is problematic. Pentane with one score of 8 is hazardous. In this system, we did not make the distinction between hazardous or highly hazardous. But solvents with one score at 10 are always highly hazardous according to the survey. The University of York has developed an Excel tool which is available in the training package and which helps you to score any solvent. All you have to do is to enter the solvent name, the physical data, and put a 1 in each column corresponding to the relevant H statements. The tool gives you the HSE scorings as well as the overall ranking by default. For the solvent which had a clear ranking according to the survey, the ranking obtained by this system is the same for 81% of solvents, which is more than acceptable. In some cases, such as dioxane, the ranking by default is less severe. For anisole, it is more severe. As the ranking methodology model is valid, it can be used to predict the desirability of any solvent. We used it first for the solvents which did not have a clear ranking after the survey, then for bioderived solvents and newer solvents, like the ethers proposed to substitute methyl tertiobutyl ether. The intermediate solvents were not easy to rank because of their unclear balance between advantages and hazards. In some cases, we did not agree with the rankings given by the simplified system. For example, methanol is ranked as problematic by default because of its alarming health statements and relatively low boiling point. But as its occupational limit values are relatively high, and as it is fully biodegradable, we decided to rank it as recommended. On the other hand, pyridine was ranked by default as recommended, but as its occupational limit values are very low, we decided to rank it as hazardous. Thus, the simplified method has its limits, and a debate associating chemists and occupational hygienists is needed to give definitive rankings. For bioderived solvents, we accepted the rankings by default. As shown in this table, many of these solvents appear as problematic as a result of their high boiling point, giving an environmental score of 7, such as 1,3-propanediol, glycerol, or ethylene carbonate. In the case of paracimene, the lack of data also results in a ranking by default as problematic. This illustrates the current difficulty to integrate these solvents in chemical processes. In conclusion, this guide is based on a survey of published solvent guides and comprises a methodology able to rank any solvent. This system uses easily available physical data and GHS hazard statements given in the REACH dossier and is aligned with the European regulations. This methodology is not perfect. The health ranking should be better based on the occupational evaluation limits, but they are not always available and not unified, even in Europe. The environment criteria should include the impact of the solvent synthesis in terms of carbon footprint or cumulated energy demand. Besides, RICH dossiers are often incomplete. This is why a discussion with experts is needed to give a definitive ranking. This work has been published in 2015 in Green Chemistry. This methodology offers other perspectives. The CHEM21 solvent guide has been designed for pharma chemical industry, but the field of green chemistry is wider, and solvent guides are needed for other applications with different criteria weight. Our system can easily be modified to fit with other constraints or requirements. For example, for coating diluents or solvents for paint stripping, the flashpoint weighing will be more severe, and the environment criterion will favor high boiling solvent, such as many bio-derived solvents.